In this video, we will be learning how direct mapping works. As the name says, direct mapping is where the blocks of the main memory are directly mapped into your cache. So here, you have block and block numbers for your main memory and your line and line numbers. So you are going to use this direct mapping where the block which is having the least significant of 0, 0 will be directly mapped to your cache. The ones which have the least significant of 0, 1 will be mapped to the cache line 1 and so on. So this is the concept of direct mapping. So for that, first let us take an example and understand how this direct mapping and the mechanism works. The number of blocks here is your main memory size by block size. The main memory here we have taken is 128 bytes. So 128 divided by the block size. The block size is nothing but the number of bytes that could be kept in a single block. So it is 8 bytes. So totally we will be having 16 blocks. Okay, we will be having 16 blocks to represent the the data. Okay, because we are using block addressable, we will be having 16 blocks. So it is 2 power 4 blocks. So using the basic formulas that we have already understood, the block index is 4. Block index is 4. So you will be using 4 bits in order to access each and every block in your main memory. Yes, so it is 0, 0, 0, 1 to 1, 1, 1, 1. This is how you will be using this block index to access. Now, we will go to the cache part. The cache size is 32 bits. So, the number of lines, we have to calculate the number of lines. Number of lines of the cache is cache size divided by block size. As I have already told, both the main memory and the cache both will have the same number of bytes. Okay, so it is 8. Because the block size is 8 for the main memory, it is going to be the same for the cache memory. So it is 32 divided by 8, which is 4 lines. We have 4 lines in the cache. It is represented as 2 power 2. So the number of bits that are required for your cache index is 2. That is why we have used 0, 0, 0, 1, 1, 0 and 1. 2 bits to access each line of the cache. This is how the direct mapping happens. You cannot directly have all the blocks which have the least significant 0 into the cache line 0. Okay, you can either have this or block 4 or block 8 or block 12 at a time in the cache line 0. Then you could have either 1 or 5 or 9 or 13, any one in this line 1. This is how direct mapping works. So in order to identify whether the respective block is there in the cache or not, there is a mechanism which is used, which is called your tag bits. Okay, we will be using tag bits to find, because we want to know whether because this line block number 0, 4, 8 and your 12, right, it should be placed, right, it should be placed into the line 1. We have to know where what block has been placed, either it is 0 or 4 or 8 or 12. We want to identify which block. For that you are using this tag bits. Okay, tag bits is nothing but it is again it's like an index. Okay, so we have to find the size of the tag bits. Tag bit size is nothing but your block index minus your cache index. So the block index size is 4 minus your cache index size is 2, so it requires 2 bits. So you are going to use 2 bits for your tag, and we have 4 cache lines here, so we will be having 4 tag lines also. Okay, so if this cache has 8 lines, you will be having 8 lines in your tag as well. Okay, this is how you should relate. Okay, now what values will be placed in this tag bits? tag bits will hold the most significant bit of the block index. So the least significant bit are used for your catch identification, and the most two bits of your block index will be used as your tag bits. Okay, it will hold the most significant bits of your block index. In this example, it is 2 bits, so the most significant 2 bits of your block index will be placed here. Okay, so if I'm going to place this block 0 here, this is block 0, right? The block 0 index is 0 0 0 0. So because it is 0 0, we are going to place the block in the catch line 0. So this corresponding full block is transferred to the catch line 0. Okay, now this most significant 2 bits are stored in the tag bit. Okay, so it is 0 0. Since each catch line has an associated tag bit, if I am going to place in catch line 0, the tag line 0 will be filled. If I am placing some value in the catch line 2, the corresponding tag line will be filled. This is how you have to understand. Okay, so here we have placed block 5. What is the value of block 5? Block 5 is 0 1 0 1. So because it is 0 1, I am going to place the block in the line 1, and the most significant 2 bits are copied to the corresponding tag lines. Since it is line 1, here also the line 1 is filled. Okay, this is how we will be filling. Now the CPU has given a request. We will now find out whether this is going to be a hit or miss. This is the block address. This is your physical address. Okay, the physical address is 7 bits in wide. Okay, the physical address is 7 bits wide. So first we will take this example. Okay, so the physical address contains the least 3 bits for your block offset and the most significant 4 bits for your block index. Block offset and block index are one which is used to index the row and the column of your main memory. Okay, this is your physical address. Now we will check whether this respective block is present in the cache or not. Now in order to access that, since we are not using the main memory, you are going to check only the cache. We cannot use the block index as such, right? This block index could not be used because we are not going to directly check with the main memory. We are going to check with the cache memory. So we are left out with only these 4 bits. Okay, we are left out with block offset is used to identify which corresponding part you want in the which corresponding part you want in the block. That we are going to use only later, so we will just ignore it now. Now we have the first 4 bits. Because the physical address first 4 bits are your block index, you cannot directly check with the main memory because we have done the mapping with the cache. It is there in the cache. Now what mechanism could be used to check if it is in the cache or not? You are going to use tag bits. Now we are left out with your cache index, which is this, and your tag bits. Okay, so we are left with only these 2 categories. So we can find out using, we can allocate suitable bits for your cache index and tag bits. So the most significant, because your block index, the most significant bits of your block index is your tag bit, you can use the most significant 2 bits as your tag bit and the next 2 bits as your cache index. Yes, we have. So I am writing the first request here to this. Okay, now I am going to check this cache index. It is 0 0, so it represents that the data or the block is present in the cache line with index 0 0. This is going to be the first cache line. Okay, this is going to be the 0th cache line. Okay, now so we have to check with the corresponding tag bit only, because each cache line is associated with the tag bit. So we are going to check with the corresponding tag bits. So the value is 0 0. Now this corresponding tag bit, which is relevant to the cache index having 0 0, is compared. You have a comparator, is compared with this, the tag bit in the physical address. Now when both are matching, it is said to be a hit. When they don't match, it is said to be a miss. Okay, now let us take this example: 0 1 triple 0 1 double 1, 0 1 triple 0 double 1. Okay, now this is the catch index is 0 0. I am going to check the 0 0 relevant tag bit. Okay, so the tag bit value is 0 0. So it is compared with the tag bit in the physical address. So what is the value? 0 1. So when you compare, it is not going to be found, hence it is a miss. This is how you will be identifying whether it is going to be a catch hit or a catch miss. Now because it is a miss, we have to replace, right? We have to replace. So how will you replace? We have to write back this corresponding, because this catch index is 0 0. The block that is not wanted by the CPU is occupying this place, right? So we have to write back this. Okay, write back this to the main memory, and we have to shift this new block because it is 0 1. Okay, it is 0 1. If the catch index is 0 0 and the tag bit is 0 1, it is nothing but 0 1 0 0, which is your fourth block in your main memory. So that has to be moved into this catch line. Okay, it is moved into the catch line, and you are going to update the corresponding catch. Okay, catch block. Now it is going to be a catch hit. If you search, it will be a catch hit. In this case, because we have moved this block, 4, the most significant 2 bits will also have to be updated in your tag bit. So when block 4 is there in your catch, the corresponding tag bit of block 4 should be updated to 0 0 1. Now let us take the same example. Now 0 1 triple 0 double 1. So you have 0 1, yes, and your triple 0 double 1. Now what will happen? We will be checking, right? This is the catch index is 0 0. So we are going to check in 0 0. The corresponding tag bit will be taken and it will be compared with this tag bit in the physical address. Both are same, so it is going to be a hit. This hit has occurred only after we have transferred one block back to the memory and replaced it with the new block. This is how you will be performing this direct mapping technique.